Alright, so let's look at this inverse Laplace problem here, right? Okay, so if you're doing these, what you want to notice is if you have an exponential, say an e to an s over here, right? Then this is an indication that what you need to do is you need to use t-shift formula, right? Okay, so this is the statement of t-shift formula, right? This here is just really a setup of t-shift, right? So Laplace of small y of t is big Y of s, right? So this is really just standard notation, right? And now this line underneath it, this is the t-shift formula, right? So if I want to get Laplace inverse of e to the minus s t0, right, times the big Y of s, right? What you do is what you do is for this big Y of s over here, once you identify it, right, you need to take Laplace inverse of that to get the small y, right? And then with that small y, what you're going to do is you're going to shift it over here and then multiply by a Heaviside, right? Okay, so let's just do it for this problem, right? So if you're doing these Laplace inverse of with the exponential here and you're using the t-shift, right? First thing you want to do is you want to identify what the t0 is, right? So the t0 is 3, right? Next thing over here is you need to identify what the big Y of s is, right? So how you want to read this is that you have the exponential times some function of s, right? And over here you have your exponential e to the minus 3s times this function 2s plus 7 on s squared plus 16, right? Okay, so that over there, this is going to be my big Y of s, right? All right, and to use t-shift, right, if I have big Y of s, right, what I would need is a small y of t, right? So what that means is I'd need to take Laplace inverse of this big Y of s, right? Okay, so this is 2s plus 7 on s squared plus 16, right? To work this out is not going to come immediately from a table, right? But there's no real need to use partial fractions over here, right? You could realize that this is 2s on s squared plus 16, and this is 7 on s squared plus 16, right? Okay, so the small y of t is the Laplace inverse of this, right? With the Laplace inverse, you could use the linearity to break this up, right? As we did over here. And then you can pull this 2 outside here, right? In this case, with the s squared on 16 here, right? And the 7 on top. What I'd want is I'd want a 4 on top here because the 16 is 4 squared. Okay, so what I do is I just adjust the constants a little bit here, right? Note the 7 on 4 times the 4 on the top just gives me back to 7, right? And the point about having this 4 over here now on top is that this Laplace inverse of the 4 on s squared plus 4 is just going to come directly from the table. This is going to be sine 4t, right? And then the Laplace inverse of the s on s squared plus 4 squared is cosine 4t, right? Okay, so this gives me what my the small y of t is, right? So that gives me what the small y is, but I still need to actually give the answer for this, right? So I still need to use the t-shift over here, right? So I know the t0, right? I know the big Y of s, and now I know the small y of t, right? But you want to notice over here what I have in for t-shift formula. This is small y, but shifted, right? So this y of t over here, what I would need to do is I'd need to shift it, right? Okay, so right. Okay, so using the t-shift here, right? I'm using t-shift, so Laplace inverse of what I was given is going to be Heaviside ht minus 3 times small y t minus 3, right? So what I worked out previously was small y of t, right? And what I need is now y of t minus 3, right? Okay, and how do you get the y of t minus 3 is in this over here, right? Everywhere you see the small t, you're just going to replace by t minus 3, right? So here I'm going to get 4 times t minus 3 over here. And here I'm going to get 4 times t minus 3, right? Okay, so this is my answer, right? It's going to be Heaviside ht minus 3 times your function yt minus 3, which consists of this cosine term here and the sine term over here. Alright, so let's consider this problem here where I want to get want to show, right, use the definition of the Laplace transform to show that Laplace of t minus 5 is 1 on s squared minus 5 on s, right? So that's a 5 on top there. right? And this holds when your real part of s is bigger than 0, right? Okay, now obviously you can really just work this out directly by using linearity and just using your table, right? But the question is asking you to use the definition of Laplace transform, right? Okay, so your definition of your Laplace transform here is Laplace of t minus 5. So what you do is you multiply the t minus 5 by the e to the minus st, and you integrate it from 0 to infinity, right? You want to recall that this here, well, when you're integrating from 0 to infinity, this is an improper integral, so our way of doing it is replace the infinity by r, and you take the limit as r goes to infinity, right? Okay, so inside over here, the integral from 0 to r, right, of this function here with respect to t, right? This is just a normal integration here, right? Okay, so we could use our usual rules, and in this case, what we need to do is you need to use integration by parts, right? Okay, so normally what you do is, what you're going to substitute for is, well, you choose your substitution, right? You choose, well, I'm using here that integral of v du is uv minus integral u dv, right? So the v, right, what I'm going to do is I'm going to differentiate it, right? So you choose something that when you differentiate, it gets simpler, right? Okay, so you could do it this, well, what you're going to choose over here is you're going to choose t minus 5, right? And that's basically what you're doing. But my point that I want to make is that you can actually expand this out, right, if you wanted to do it that way, right, and then work them out separately. But that's actually too much work, right? It's easier here just to simply say that the v is equal to t minus 5, right? Okay, so once you have the v, you do what you normally do for integration by parts, you differentiate, right? Okay, so when you differentiate the t minus 5, you're going to get 1. So you get dv dt is equal to 1, which means that the dv is equal to dt, right? Okay, and if you choose the v is equal to t minus 5, then the du is going to be everything else, right? Which is e to the minus st times dt, right? And if the du is equal to the e to the minus st times dt, how you get the u is you get the u by integrating this right-hand side over here, right? Okay, so integrate e to the minus st, which is e to the minus st on minus s, which is how I get this u here, right? Alright, okay, so I use my integration by parts formula, right? Recall what I'm doing is I'm integrating between 0 and r over here, right? So the integral between 0 and r here, I use the integration by parts formula, right? So I have uv, right, which is the e to the minus st on s times the t minus 5 here, right? And then I have integral of u dv, right? And that's the integration by parts formula. It's minus integral of u dv, right? So the minus in the formula will cancel with this minus to give me a plus, right? The 1 on s over here I pull outside, right? And then I have e to the minus st, right? And here I need to integrate between 0 and r, and with this uv over here I need to evaluate at 0 and r here, right? Okay, right, so I get to this point here, right? And let me evaluate at t is equal to 0 and t is equal to r, right? Okay, so you simply just substitute t is equal to r into this, so I get e to the minus sr over here, right? R minus 5 on the s here, right? And then I put in the t is equal to 0, right? So I'm going to get e to the 0, which is 1, right? And multiplied by minus 5 on s, right? So this is an s on the bottom here, right? Okay, and I still need to evaluate this at t is equal to 0 and t is equal to r, right? Alright, so evaluating at t is equal to 0, right? Okay, so evaluating at r over here gives me minus e to the minus sr and s squared, right? Which is this over here, right? And evaluating at t is equal to 0 gives me e to the 0 here, which is 1, right? And it's so minus 1 on s squared, right? But for your lower limit over here, of course, you're subtracting, right? So you're going to get a minus minus, which gives me this plus 1 on s squared here, right? All right, so I get to this point here, right? my Laplace of t minus 5 is equal to the sum of these two limits, right? Now what I need to do is I need to work out these limits here, right? Okay, so you want to, over here I have 5 on s, right? Minus 5 on 1 on s squared, right? Okay, so you want to notice that both of those are independent of r, right? So if I'm taking the limit of those, for example, if I'm taking the limit of minus 5 on s with respect to r, that's just going to be equal to the minus 5 on s, right? And taking the limit of 1 on s squared with respect to r just gives me the 1 on s squared, right? Okay, but I still need to work out these two limits over here. This one involves r, right? So e to the minus sr times r minus 5 on s, which is this one over here. And this guy over here, which is e to the minus sr on s squared here, right? Okay, so in this question, they in fact gave you that your real part of s is bigger than 0, right? Okay, so you want to show that this is true, right? When your real part of s is bigger than 0, right? So we can use that information here, right? Sometimes they may ask you to get your region of convergence, but in this case, they in fact gave it to you, right? Okay, so let's use that over here, right? We given that the real part of s is bigger than 0, right? Okay, so what does that mean for us, right? Well, let's look at this limit over here of the e to the minus sr on s squared over here, right? Now, this s over here is complex, right? So the s, remember we talked about this, the s you can write as sigma plus j omega, right? So it has a real part and an imaginary part over here, right? Now, when your real part of s is bigger than 0, right? What that means is that the limit of the e to the minus sr is going to actually be equal to 0, and let's see that, right? Okay, so your e to the minus sr, you write the s as sigma plus j omega. This is exponential with a sum of powers over here, so you can split this up as a product of exponentials, right? The e to the minus j omega r over here, right? I can use the Morse theorem to write that as cos omega r plus j sine omega r. This is being multiplied by an exponential, right? Now actually right here, this is sort of good enough to see that this limit is going to head to 0, right? Because if the sigma, right, over here, so the real part of the s over here is equal to sigma. If that is bigger than 0, right, then what you have is you have an exponential here with r over here and a negative number in front of it, right? Now that sort of exponential, right, the limit of that will head to 0 here, right? Okay, so overall this entire thing is going to go to 0 because anyway the cos and the sine over here really are bounded between 1 and minus 1, right? So this over here is what forces the limit down to 0, right? And in fact we saw that previously, right? This is sigma minus 3, but it's the same idea. Forget about the fact that we have sigma minus 3. It's really the same sort of idea, right? So in this case, the e to the minus sigma r, right? When the sigma is bigger than 0, means I'm going to have you're going to have an exponential with negative r over here, right? And what that would mean is, for example, with the e to the minus sigma r cos omega r, you have a sinusoidal that's like this over here, that's decaying down to 0, right? Okay, so this expression over here is trapped between envelope formed by the exponentials, and that's why it's going to head to 0, right? That's, you could look at it that way graphically, but really what's happening over here is that the e to the minus sigma r, as r goes to infinity, because the sigma is bigger than 0, the minus sigma is negative, right? In which case your exponential over here is just going to head to 0. And 0 times everything else over here will just push it down to 0, which is how I get the 0 over here, right? Okay, so that explains why this limit over here, as r goes to infinity, this limit over here will drop to 0 here, right? But what about this one, right? Well, what's happening over here, notice over here, again I have e to the minus sr, right? So the e to the minus sr this one is going to head to 0 over here, but the r minus 5, as r heads to infinity, that's going to go to infinity, right? So what you have is you have 0 times infinity over here. Right, and you want to recall that 0 times infinity is an indeterminate form, right? So how you deal with that is you want to use L'Hopital's rule, right? Which means that you're going to be differentiating the top and the bottom, right? So this e to the minus sr, I'll put it down on the bottom as e to the minus sr. I'll put it down on the bottom as e to the sr, right? And now how you work this out using L'Hopital's is you differentiate the top and you differentiate the bottom, right? So differentiating the top gives me 1, right? And differentiating the bottom over here gives me s squared e to the sr, right? Okay, this 1 on s squared e to the sr, right? What I could do is, well, let's see, now I was working with e to the minus sr. I'll take this e to the sr and put it back on the top, right? So what I have is e to the minus sr on s squared here. I can pull out the 1 on s squared, right? But the main thing over here is this e to the minus sr over here. This is going to head to 0, right? So this limit here of 1 on s squared e to the sr, this would also head to 0, right? So this one goes to 0, this one goes to 0 when the real part of s is bigger than 0. So what I'm left with is my answer, which is 1 on s squared minus 5 on s, right? And that's what I wanted to show, right? I wanted to show that the limit, the Laplace transform of t minus 5 is 1 on s squared minus 5 on s when your real part of s is bigger than 0. Alright, so let's do this differential equation problem with given initial conditions, right? So we want to solve this using Laplace transform, right? Okay, so remember what the method is. You take Laplace transform on both sides, right? This is a 5 over here, so it's a 5t, right? What you do is you use your linearity to break this up, right? And when you use your linearity, what you're going to have is you're going to have Laplace of y double prime minus 10 Laplace of y prime plus 9 Laplace of y, right? Going from here to here, well, what I did is I directly used the formula of Laplace of second derivative, right? So as I said, you use your linearity to break this up, and what you'd have is a Laplace of y double prime, right? And the formula for the Laplace of y of double prime is this over here, right? S squared Laplace of y minus sy0 minus y prime 0, right? And then I have minus 10 Laplace of y prime, and here I use my formula for Laplace of y prime, and then I have 9 Laplace of y, right? And in this case, your right hand side over here is not piecewise defined or anything. It's just a very easy function, 5t. So your Laplace of 5t here, you can just get from your table, which is 5 on s squared, right? And now what I have is I have this here, right? And the next step is, notice I have this y0 and y prime 0. So I want to put in the initial conditions that are given to me, right? Right, the y0 is equal to minus 1, right? So I'm going to get minus 1, which is plus 1 here. So I get plus s, right? And the y prime 0 is 2, right? So I put that in. I have a minus 2 here, right? Likewise over here, the y0 is equal to minus 1, right? So I'm going to have minus 1, which is plus 1, but that's going to be multiplied by minus 10, so I got a minus 10 here. And then I have the minus 10s Laplace of y here, right? Okay, so I have this expression here. And now, when you're doing these problems, the next step is to solve for Laplace of y, right? Okay, so everything that doesn't involve the Laplace of y, right, which is this s, the minus 2 and the minus 10, right? What you want to do is you want to move that across to the right hand side, right? So I'm going to have this 5 on s squared, which was there before, right? And then this s will move across as minus s, and the minus 2 and the minus 10, which is minus 12. When I move it across on the side, it's 12, right? Okay, so, and then I have, what I'm left with is terms just involving Laplace of y, right? Which is the s squared Laplace of y, the minus 10s Laplace of y, and then the 9 Laplace of y, right? And with that, I can factor out the Laplace of y. And when I factor out the Laplace of y, I get Laplace of y times s squared minus 10s plus 9, right? And then what you do now is you well, you're solving for the Laplace of y, so you just divide by the divide throughout by s squared minus 10s plus 9, which gives me this over here, right? Notice what I'm doing here is I'm taking a common denominator here with this s squared and the s squared minus 10s plus 9, right? So how you could look at this is, if this was, I had 5 minus s cubed plus 12s squared all on s squared here, right? And then I divided by s squared minus 10s plus 9, right? Okay. Alright, okay, so I have that so far, and given this here, what I need to do is to get the y, which is the objective. You want to solve your differential equation, right? So solving the differential equation is figuring out what the y of t is, right, for the given initial conditions. Right, so to get the y here, I need to take Laplace inverse of this right hand side, right? And obviously this here is not going to come directly from a table, so what you're going to do here is you're going to use partial fractions, right? This s squared minus 10s plus 9, right? This will factorize as s minus 1 times s minus 9, so I may as well do that, right? Okay, and what I have is I just have linear factors here, right? Okay, so so the form of my partial fraction expansion is given over here, right? I have a repeated s squared here, so I'm going to have a on s plus b on s squared. And then for this s minus 1, I have c on s minus 1. And then for the s minus 9, I have d on s minus 9. Right? Okay, so you clear denominators now, right? So in other words, you multiply both sides of the equation by your denominator here, which is s squared times s minus 1 times s minus 9, right? And once you have this, what you need to do is you need to solve the constants, right? So solve for the big A, the big B, the big C, and the big D, right? Okay. Alright, so how we solve for the A, the B, the C, and the D, right, would be substitute values, right? Okay, so if we substitute s is equal to 0, right, well, the term with the A will drop off, the term with the B, and the term with the A will drop off, the term with the C will drop off, the term with the D will drop off, right? What you'd be left with is B times minus 1 times minus 9, right, which gives me 9b over here. And then on this side over here, what I'm going to have is 5, right? So I get 5 is equal to 9 times b, which gives me b is equal to 519, right? Okay, and then I can substitute s is equal to 1, right? When I substitute s is equal to 1, the term with a will drop off, term with b will drop off, term with d will drop off, and what I'm left with is I'm left with right, 1 times minus 8 over here, right? So I have a minus 8c, right? And on this side over here, I have right, I have minus 1, right, plus 12, right, plus 5, right, which is 16, right? So I have 16 is equal to minus 8c, and that gives me c is equal to minus 2. Okay, similarly, I put in s is equal to 9, the term with a will drop off, the term with b will drop off, the term with c will drop off, and I'm left with this expression in the d, right? Okay, so putting in the 9 over here gives me 81 times 8 over here, right? And putting in the 9 over here, right, gives me minus 729, right, plus 972 plus 5, which is this, right? And you really just work this out, right? So your left-hand side over here works out to be 248, right? Okay, over here I have 81 times 8, and I can divide throughout by 8, so I'm going to have 31 on this left-hand side and 81 on 81d on this right-hand side, and that gives me that the d is equal to 31 on 81, right? Okay, right, so, well, okay, that gives me b, C and D, right? I want to notice you can't actually substitute, right? So you can substitute any value you want aside from 0, 1, and 9, right? And that would again give you an equation in A, B, C, and D, right? But it's probably easier here if I look at what do I want to find, right? I have the B, the C, and the D already, right? What I want is a term. I want the A over here, right? Right. So I want to get the A over here, right? So what I'm going to do is, instead of substituting values, I'm going to compare the S cubed terms, right? So there's a typo in this notes over here, right? This shouldn't be S squared. This should be S cubed, right? Okay, so we're looking at the term in the S cube right now. Where do I have an S cube, right? Well, over here on this left-hand side, I have S cubed over here. So the coefficient of the S cubed here, the minus S cubed is -1, right? So that's where I get this -1. Okay, so the coefficient of the S cubed is -1, right? So that's where I get this -1 here. Okay, now I want to find the S cubed coefficient from the right hand side, right? Now notice here I'm going to have A, right, times an S, an S, and an XS, right? So I'm going to have an AS cubed over here, right? This for the B over here, right? You're not going to have any S cubed term, right? Over here, however, you're going to have a CS cubed, and over here you're going to have a DS cubed, right? So you're going to have A plus C plus D, right? S cubed, right? So the coefficient of the S cubed from this right hand side here is A plus C plus D, which is this, right? Okay, so that would allow me to figure out what the A is, right? Because I know what the C is already and I know what the D is already, right? So I substitute my values for C and D into this. Okay, so substitute the values for C and D, right? Okay, well, first thing I did is rearrange, so I have that the A is equal to -1 minus C minus D. Okay, and then I put in the C and the D, right? The C is -2, so I'm gonna get -2, which is +2, and the D is equal to 31 on 81, right? Okay, so when I work that out, I will get that the A is 50 on 81, right? Okay, so my partial fraction expansion, the A is 50 on 81, right? The B is 5/9, right? The C is equal to -2 and the D is equal to 31 on 81, right? Okay, so that's my Laplace of y, right? And to get the y, what I'm going to do is take the Laplace inverse of this, right? Now, while it might look a little complicated, remember the constants are not doing anything for you, right? So you're gonna, when you're taking the Laplace inverse, you're using the linearity of Laplace inverse to break this up, right? So you'll take 50 times 81, Laplace inverse of 1 on s, which is 1, right? So I'm going to get 50 on 81 times 1, right? Then 5 on 9 times Laplace inverse of 1 on s squared, which is t, right? So I get 5/9 times t, right? And then -2 times Laplace inverse of the 1 on s minus 1, right? And Laplace inverse of the 1 on s minus 1 is e to the t, right? So I get -2 e to the t. And then finally, Laplace inverse of the 1 on s minus 9 is e to the 9t. So I'm going to get 31 on 81 times e to the 9t, right? Okay, so that's the solution of my given differential equation, right? Solution of this differential equation is this expression here, right? 50 on 81 plus 5/9 t, right? Minus 2 e to the t plus 31 on 81 e to the 9t. Alright, so let's look at this problem here, right? You're given a function, right? That's a sum of two Heavisides. We need to graph it and then find Laplace of it, right? Now finding Laplace of this is easy, right? Because you just use your linearity, and then Laplace of the ht minus 1 is just going to come from a table, and likewise Laplace of the ht minus 3 is just going to come from a table, right? Okay, so the hard part over here, if it's hard, right, is really to graph this, right? Okay, so we want to graph this ht minus 1 plus ht minus 3, right? Now what you want to notice with what you're going to have is you have a change in behavior at t is equal to 1 and then at t is equal to 3, right? So what that means is if you're going to graph this, you're going to want to consider right, what you're gonna have a certain behavior from 0 to 1, you're gonna have a next behavior from 1 to 3, and then you're gonna have a third behavior from 3 onward, right? From 3 to infinity, right? Okay, so the fact that you have a change in behavior at 1 and a change in behavior at 3, right, means I'm gonna have 3 intervals that I need to look at, right? 0 to 1, right? 1 to 2, 1 to 3, right? And then 3 to infinity, right? So I put that down in my table, right? Okay. And now what I want to graph is I want to graph ht minus 1 plus ht minus 3, right? Okay, so I'll do it in steps, right? First, need to put in the, I want to determine the values of the ht minus 1 on my 3 intervals, right? 0 to 1, 1 to 3, and then 3 to infinity, right? Now let's recall what your graph of what the Heaviside is, right? So the Heaviside is, right, before t0 is equal to 0 and after t0 is equal to 1, right? So in this case, the t0 is equal to 1, right? So before 1, your function is going to be equal to 0, and then after 1, the function is going to be equal to 1, right? So that's how I get a 0 over here, and then after 1, it's equal to 1, right? Okay, and similarly for the ht minus 3, right? Before 3, it's before the 3 over here is equal to 0, right? So in the interval 0 to 1, right, that's going to be 0. From 1 to 3, that's going to be 0. But then after 3, it's going to be 1, right? So that's how I get this here, right? Okay, and so I have, for each interval, I have the value of ht minus 1 on that interval and ht minus 3 on that interval, right? Okay, so between 0 and 1, this function over here, ht minus 1 plus ht minus 3, right? Well, between 0 and 1, the ht minus 1 is equal to 0, and the ht minus 3 is equal to 0, so what I have is 0 plus 0 is equal to 0, right? Between 1 and 3, right, the ht minus 1 is 1, right, and the ht minus 3 is 0, right, so I'm going to have 0 plus 1, which is 1, right? And from 3 to infinity, the ht minus 1 is 1, the ht minus 3 is 1, so I'm going to get 1 plus 1, which is a 2 over here, right? Okay, so once I have the table, now I can graph. Okay, and it's not hard, right? So between 0 and 1, right, function is equal to 0, right? Notice over here, this is strictly less than, so I have an open dot over here. Between 1 and 3, the function is equal to 1, right? And notice I have a closed dot over here, right? Okay, so between 1 and 3, function is equal to 1. And then from 3 to infinity, right, including the 3, right, the function is equal to 2, right? Okay, so this is my required graph, right? And getting the Laplace of the f of t is easier, right? You just take Laplace of the ht minus 1, ht minus 3, right? You use the linearity to split this up, and this really just comes from your table, right? Laplace of ht minus 1 is e to the minus s on s, and Laplace of ht minus 3 is e to the minus 3s on s. Alright, so let's consider this problem over here, right? They give me the graph of a function, right? And they ask me to write this f of t in terms of Heavisides, right? And then determine Laplace of f of t, right? Okay, so this is a little different from the type of problems that we probably would have seen before, right? This here is right, typically what you're given is you're given a piecewise defined function, right? And you say you want to get the graph of it, right? Now what you're given is you're given a graph here, right? And you want to get the piecewise defined, well, in order to express it in terms of Heavisides, first you'd need to get express the function, right, as a piecewise defined function, and then express it in terms of Heavisides, right? So that's the idea there, right? Okay, so first thing is I want to express my function as a piecewise defined function, right? And you see in what the intervals are here, right? You see in it's 0 to 2, right? So the 0 to 2, right? From 2 to 3, right? You have a certain behavior, right? From 2 to 3. Then from 3 to 4, you have a different behavior. And then it's 0 from 4 onwards, right? So you have 4 intervals over here, right? 0 to 2, 2 to 3, 3 to 4, and then 4 to infinity, right? Okay, so, and then from the graph, well, notice between 0 and 2, your function is equal to 0, right? Let's do the easy one, right? Between 3 and 4, right, your function is equal to 1, right? From 4 onward, the function is equal to 0 here, right? But from 2 to 3, what you have is, you have, this is a straight line over here, right? Between 2 and 3, right? Okay, so you want to notice, well, for one thing, well, in order to get the function over here, right, what you need to do is you really need to get the equation of the straight line passing through these 2 points, right? Passing through the point 2, 0 and the point 3, 1, right? But an easy way to see this is, well, right, you want to notice, well, okay, a slope over here is equal to 1, right? Because the difference in the y values is 1 over here, and the difference in the x values is 1, right? So your slope is equal to 1. Now, if you take this and you extrapolate it back over here, right, what it would do is, if you use a certain amount of symmetry, you'd realize, and the fact that the slope is 1, you'd hit your y-axis at -2, right? So what that means is that the equation of this line over here is in fact going to be equal to t minus 2, which is this here, right? Okay, now if you're not happy with that reasoning, you could really just find the equation for using the 2 points, right? 2, 0 and 3, 1, right? Okay, so I get my function f of t is piecewise defined, and it's equal to 0 between 0 and 2, between t minus 2, between 2 and 3, right? It's equal to 1 between 3 and 4, and equal to 0 between 4 and infinity, right? Okay, so this is it as a piecewise defined function, but now I want to express it in terms of Heavisides, right? It probably mightn't be very easy to just go from the f of t to the Heavisides. It's not impossible, right? But it might be easier to, if you're doing this, to do it as I did, right? To have the f of t, right? Express the f of t as a piecewise defined function and then convert it into a form using Heavisides, right? Okay, and remember how we do that, right? How you express, right? If a piecewise defined function in terms of Heavisides is that, well, notice over here, this sort of formula here actually has 4 different intervals, which is exactly what I have across here, right? So essentially, I'm going to be using this formula here, right? Okay, so it's going to be 1 minus a Heaviside times my original function, right? So it's 1 minus the Heaviside, and then the value over here is the endpoint of this interval, which is 2, right? So 1 minus Heaviside times 0, right? And then a difference of Heavisides times t minus 2, right? Okay, and it's ht minus 2 and ht minus 3, where the 2 and the 3 are coming from over here, right? And then it's a difference of Heavisides times this function, which is 1, right? And then finally, just a Heaviside by itself times your function over here, which is 0, right? This value here, which is 0. Okay, right, so I have this, and now what I should do is probably just clean it up a little bit, right? Here, this is ht minus 2 times t minus 2, right? Then it's minus ht minus 3 times t minus 2, right? Okay, but I also have this ht minus 3 over here, right? So this is minus ht minus 3 times the t minus 2, right? And then this minus ht minus 3 times this minus 1 is plus ht minus 3, which is this over here, right? So basically what I'm doing is I'm taking this ht minus 3 and I'm merging it with the ht minus 3 times t minus 2 over there, right? Okay, and then what the last thing I have over here is minus ht minus 4, which is this, right? Okay, so you want to notice, right, so now that I have this t minus 2, right, minus 1 is now t minus 3, right? So I have my f of t expressed in terms of Heavisides this way, right? And this here, now I can use T shift, right? And I can use my normal version of T shift, right? So which is this over here, right? Okay, so Heaviside times a function over here that is shifted, right? So when you take in Laplace of that, it's going to be exponential times Laplace of the unshifted function, right? So here in this case, I'm going to have a e to the minus 2s, right? So the t0 for this guy over here is 2, right? And then this t minus 2, what you want to do is you want to unshift it, right? Okay, so this yt minus t0 in this formula here, what you do is you unshift it and then you take Laplace of it, right? Okay, so that's what I'm going to do over here. This t minus 2, I unshift to get t, and then I take Laplace of t, which would give me 1 on s squared, right? And similarly over here, right, using the same t shift formula, I'm going to get e to the minus 3s on s squared, right? And this one over here, well, you could use t shift, but really this would just come straight from a table, right? So Laplace of the ht minus 4 is e to the minus 4s on s. Okay, and this is my answer, right? Laplace of f of t is equal to this right-hand side. Alright, so let's consider using a Laplace transform to solve our next differential equation, right? This one is a little more challenging, right? Okay, so you do what you normally do. You take Laplace transform on both sides. Notice this right-hand side over here, this is piecewise defined, right? So this g of t here, piecewise defined, I can express in terms of Heavisides, right? Call that, well, in this case, what you have is you have a starting interval, you have an end interval, and you have nothing in between, right? So for your starting interval over here, it's going to be 1 minus a Heaviside times this function cosine 40, right? And then for your ending interval, it's going to be 0 times a Heaviside, right? But 0 times this Heaviside over here is just going to give me 0, right? So what I'll have to express this g of t in terms of a Heaviside, right, would just be 1 minus a Heaviside times this function cosine 4t, which is what I have over here, right? Okay, so 1 minus the Heaviside, the g of t, I can write as 1 minus the Heaviside times cosine of 4t, right? Okay, so right, I'll take Laplace transform on both sides. Here I have Laplace of y double prime, right? And Laplace of y double prime, I use my formula for Laplace of y double prime. And then plus 16 Laplace of y, which is this over here, right? Okay, so I put in my initial conditions. My initial conditions are that y0 is equal to 0 and y prime 0 is equal to 1. So I'm going to get a minus 1 over here, right? And I still need to work out this the Laplace of this right-hand side over here, right? Okay, so I expand this, right? I have cosine of 4t times ht minus pi times cosine of 4t, right? Okay, so I'd have cosine of 4t, and notice the ht minus pi times the cosine of 4t, right? What I did over here is I wrote the cosine of 4t as cosine of 4t minus pi, right? Now really what I'm doing there is I'm just using the fact that cosine is periodic of period 2 pi and also 4 pi, right? So cosine of 4t minus pi, right, is cosine of 4t minus 4 pi, right? And that's just the same as cosine of 4t, right? Now why I want that is I want this expression here. I want a t minus pi over here to match the ht minus pi over there, right? Okay, right. And I can take Laplace now of my right-hand side over here. So I have Laplace of cosine of 4t, which is just s on s squared plus 16. And over here, what I'm doing is I'm using t shift, right? So remember to work out Laplace of this Heaviside times this cosine, which is shifted here, right? What you do is you multiply by the exponential e to the minus pi s over here, and then you unshift this cosine 4t minus pi to get you cosine 4t, right? And then you take Laplace of that, right? Okay, so once I have this now, what I need to do is I need to solve for Laplace of y. So I take this minus 1, move it across on this side, and then I'm dividing throughout by s squared plus 16, right? Okay, so recall I have a plus 1 now on this right hand side, and that 1 divided by the s squared plus 16 gives me the 1 on s squared plus 16, right? And now I also have an s on s squared plus 16, and so when I have this s on s squared plus 16 and then divide by the s squared plus 16, I'm going to get s on s squared plus 16 squared, right? And likewise over here, I'm going to get s on s squared plus 16 squared, right? Okay, so to work this out, what you could do is you could use a partial fraction expansion for this, right? This is a repeated quadratic factor, right? So you could use a partial fraction expansion for this, but in this particular case, they in fact gave you a hint, right? Notice they told you that Laplace of t sine at is 2as on s squared plus a squared squared, right? And that really is the form of what I have over here, right? The 2a is just a constant, so that's not really the big deal. The main thing here is s on s squared plus a squared squared, right? Which is what I have over here, right? Okay, so to work out Laplace inverse of this over here, I could really just use this formula, right? Alright. Okay, so I want to use this formula, so I'm going to rearrange things a little bit, right? The normal thing for the 1 on s squared plus 16, because this is 4 squared, I want a 4 on top there, right? And I multiply by a quarter here, right? So the quarter times the 4 just gives me back to 1, right? Okay, and I do something similar over here, but I want it of in this form 2as on the top, right? Okay, so the a in this case, notice this is a squared over here, so the a in this case is 4, right? So I want a 4s over here, then multiplied by a 2, which is what I have, right? Now that would give me 8s. Now over here I had s, right? So in order to make sure I just have s, in order to preserve the equality, what I do is I multiply by 1/8, right? Okay, and likewise over here I write this s on s squared plus 16 squared as 1/8 times 2 times 4s on s squared plus 4 squared squared, right? Okay, so my answer is, this is the Laplace of y, right? So to get the solution for my differential equation, right, I need to solve for the y, which means I'm going to take Laplace inverse of this right hand side, right? So you take Laplace, you use linearity, so you're taking Laplace of the individual terms here, right? Alright, so Laplace inverse of this over here, right? Inverse of this is sine 4t, so this is a mistake over here, and that should be sine 4t there, right? Alright, and now the Laplace inverse of this here, right? Really, I'm just going to use the table, right? You not use the formula here, right? Okay, so the a over here is, the small a is equal to 4, right? So the small a is equal to 4, right? Okay, so Laplace inverse of the 2 times 4s on s squared plus 4 squared squared, right? That would be t times the sine 4t, right? Which is what I have over here, right? Okay, and then I need to get Laplace inverse of this here, the exponential times this function of s over here, right? Okay, so to do this, you need to use t-shift, right? And when you're using t-shift for your Laplace inverse, you need to identify the t0, so the t0 is equal to pi, right? You need to identify what the function is over here, so the function is 2 times 4s on s squared plus 4 squared, which is this over here, right? Okay, and so Laplace inverse of this expression here inside the bracket is going to be ht minus pi times xt minus pi, right? Where this small x over here, x of t, is Laplace inverse of the big X of s, right? Okay, so first thing over here, I'd need small x of t, right? But small x of t is the Laplace inverse of this. And we worked out this already, right? That's coming from the formula that was given, right? So the small x of t is t sine 4t, right? Alright, so Laplace inverse of this exponential times this function here is ht minus pi times xt minus pi, right? Okay, so from this x of t, I will get my x of t minus pi. So I'm going to get t minus pi here times sine 4t minus pi, which is what I have here, right? So one more time, x of t minus xt here is t sine 4t, right? And to get xt minus pi, right, I just, everywhere in this equation, I replace the t by t minus pi. So I have xt minus pi over here times t is equal to t minus pi times sine 4 times t minus pi, which is what I have here, right? Okay, so Laplace of y is equal to this, and then the y of t is the Laplace inverse of this expression, which is what's shown over here on this right hand side.